Hello friends, welcome to my lecture on the concept of duality. One of the most important and interesting concepts in linear programming is the duality. Every linear programming problem has associated with it another linear programming problem which involves the same data and is closely related to the optimal solutions. Such two problems are said to be duals of each other. While one of these problems is called the primal problem, the other one is called the dual problem. The importance of the duality concept is due to the two main reasons. Firstly, if the primal contains a large number of constants and a smaller number of variables, then the labor of computation can be considerably reduced by converting it into the dual problem and then solving it. Because if there are say m constants and n variables and m is greater than n, then when we will consider the corresponding dual problem, there the number of constants will become n and the number of variables will become m. Okay. So, number of constants will reduce when we consider the dual problem, and therefore, it will be easier to solve the get the solution of the dual problem. So, labor of computation can be reduced by converting the problem into the corresponding dual problem and then solving it. Secondly, the interpretation of the dual variables from the cost or economic point of view proves extremely useful in making future decisions in the activities being programmed. Now, let us consider the following LPP: maximize z equal to C 1 x 1 plus C 2 x 2 and so on C n x n subject to these m constants a 1 1 x 1 plus a 1 2 x 2 and so on a 1 n x n less than or equal to b 1, a 2 1 x 1, a 2 2 x 2 and so on a 2 n x n less than or equal to b 2, and then the mth constant a m 1 x 1 plus a m 2 x 2 and so on a m n x n less than or equal to b m. x 1 x 2 x n are all non-negative. Now, in order to construct the dual problem, we adopt the following guidelines. The maximization problem in the primal becomes the minimization problem in the dual and vice versa. Less than or equal to type of constants in the primal become greater than or equal to type of constants in the dual and vice versa. The coefficients C 1, C 2, C n in the objective function. The coefficients C 1, C 2, C n in the objective function of the primal become b 1, b 2, b m. Okay. So, C 1, C 2, C n will be replaced by b 1, b 2, b m. Okay. These b 1, b 2, b m, and x 1, x 2, x n will be replaced by new variables by 1, by 2, by m. Okay. So, the dual problem in the dual problem maximization will be replaced by minimization, and we will have minimization of z star, where we will have z star equal to b 1 by 1 plus b 2 by 2 and so on b m by m. Okay. If the primal has n variables and m constants, like here we have n variables x 1, x 2, x n and m constants given by these m inequalities. Okay. So, then the dual will have m variables and n constants, that is the transpose of the body matrix of the primal problem gives the body matrix of the dual. So, here the body matrix is this one, body matrix is a 1 1, a 1 2 and so on a 1 n, a 2 1, a 2 2, a 2 n and so on a m 1, a m 2 and so on a m n. This is body matrix, okay, of the primal problem. In the dual problem, this will be replaced with a 1 1, a 2 1 and so on a m 1, a 1 2, a 2 1, a m 2. Okay. And then lastly a 1 n, a 2 n and so on a m n. Okay. So, here we have m rows and n columns. So, this is m by n matrix. Here we have n rows and we can see we have there are 1, 2 and so on m columns and n rows. So, n by m. Okay. So, here the body matrix it is m by n size, here it is of the size n by m, transpose of the body matrix of the primal problem. Okay, so transpose of the body matrix of the primal problem gives the body matrix of the dual. The variables in both the primal and dual are non-negative. Okay. So, now the dual problem will then be, you see here, the dual problem will now be Z star minimization of Z star equal to B 1 by 1 plus B 2 by 2 and so on B m by m, subject to the constants A 1 1 by 1 plus A 2 1 by 2 and so on A m 1 by m less than or equal to C 1. Okay. A 1 2 by 1, A 2 1 by 2, A m 2 by m less than or equal to C 2 and so on A 1 n by n, A 1 n by 1, A 2 plus A 2 1 by 2 and so on A m n by m less than or equal to C n. Okay. So, we will have these equations A 1 Z minimization of Z equal to B 1 by 1, B 2 by 2, B m by m subject to the constants A 1 1 by 1 plus A 2 1 by 2, A m 1 by m greater than or equal to less than or equal to will be replaced with greater than or equal to in the dual. So, we will have greater than or equal to here. So, greater than or equal to C 1, greater than or equal to C 2 and greater than or equal to C n, and by 1 by 2 by m are non-negative variables. Okay, let us find the dual of the following LPP. Okay. So, we have Z equal to 3 x 1 minus 2 x 2 plus 4 x 3 subject to 3 x 1 plus 5 x 2 plus 4 x 3 greater than or equal to 7. Since the problem is of minimization, you can see here, since the problem is of minimization. Since the problem is of minimization, all the constants must be of greater than or equal to type. All the constants must be greater than or equal to type. Okay. So, greater than or equal to type. So, so here what is happening is this constant, this is less than or equal to type. So, we have to convert it to greater than or equal to type. So, when you convert it to greater than or equal to type, it will become minus 7 x 1 plus 2 x 2 okay, plus x 3 greater than or equal to minus 10. Okay. Minus 7 x 1 plus 2 x 2 plus x 3 greater than or equal to minus 10. Okay. Now, so let us write the dual problem. So, maximization of maximize Z will be replaced by some W equal to, now this is C 1, C 2, C 3, they will be replaced by with B 1, B 2, B m. So, 7 by 1 plus 4 by 2 minus 10 by 3 okay, and then 3 by 4 okay, and then we will have so this is our objective function in the dual problem, and subject to the constants we will have now the matrix here is body matrix is 3 5 4 okay, 6 1 3 okay, then we have minus 7 2 1 okay, we have 1 minus 2 5. This is body matrix in the primal problem. So, in the dual problem we have to take transpose of this. So, we will have subject to constants 3 by 1 plus 6 by 2 minus 7 by 3 plus by 4 and less than or equal to, we will have less than or equal to C 1, C 1 is 3 okay. Then we have 5 by 1 plus by 2 plus 2 by 3 and we get minus 2 by 4 less than or equal to minus 2 okay, and then 4 by 1 plus 3 by 2 plus by 3 plus 5 by 4 less than or equal to 4. Okay. So, C 1, C 2, C 3, okay. And by 1, by 2, by 3 greater than or equal to 0. So, this is our dual problem. We replace minimization by maximization. The variable z will be replaced by some other variable, variable. So, we can write it as w. Okay. Then these C 1, C 2, C 3 are replaced with B 1, B 2, B 3, B 4. Okay. So, B 1 is 7, B 2 is 4, B 3 is minus 10, B 4 is 3. Okay. And we use new variables by 1, by 2, by 3, by 4. So, 7 by 1 plus 4 by 2 minus 10 by 3 plus 3 by 4. The body matrix here is 3 5 4 6 1 3 minus 7 2 1 and then 1 minus 2 5. We take transpose of this and then it becomes transpose of this becomes 3 6 minus 7 1 5 1 2 minus 2 4 3 1 5. Okay. So, we get the constants as 3 by 1 plus 6 by 2 minus 7 by 3 plus by 4 less than or equal to C 1, 5 by 1 plus by 2 plus 2 by 3 minus 2 by 4 less than or equal to minus 2, 4 by 1 plus 3 by 2 plus by 3 plus 5 by 4 less than or equal to 4. So, this and where by 1 by 2 by 3 are non negative. So, this is the dual problem. Okay. Now, let us consider the problem where we have to maximize z equal to C 1 x 1 plus C 2 x 2 and what we have here the change here is that one constant is an equality. Okay. There is a equality constant a 1 1 x 1 plus a 1 2 x 2 equal to b 1. So, how we will find the dual of this LPP. Okay. So, what we will do is the equality constant a 1 1 x 1 plus a 1 2 x 2 equal to b 1 can be written as a 1 1 x 1 plus a 1 2 x 2 less than or equal to b 1 and a 1 1 x 1 plus a 1 2 x 2 greater than or equal to b 1. Since the problem is of maximization, okay, all the constants should be of less than or equal to type. Okay. So, first constant will be a 1 1 x 1 plus a 1 2 x 2 less than or equal to b 1. The second constant, this one will be converted into less than or equal to type and we will write it as minus a 1 1 x 1 minus a 1 2 x 2 less than or equal to minus b 1. So, now the problem will this be replaced by a 1 1 x 1 plus a 1 2 x 2 less than or equal to b 1 minus a 1 1 x 1 minus a 1 2 x 2 less than or equal to minus b 1, okay, and a 2 1 x 1 a 2 2 x 2 less than or equal to b 2. Okay. Now, so when we write the dual problem here, we write maximization be replaced by minimization, minimize w equal to, now here we have b 1 minus b 1 b 2. Okay. So, we write b 1 okay, we can write b 1 by 1 dash, okay, b 1 c 1 c 2 will be replaced with b 1 minus b 1 and b 2. So, b 1 by 1 dash minus b 1 by 1 double dash, let us take the variables by 1 dash by 1 double dash and then b 2 by 2. Okay. So, this and then the body matrix is now a 1 1 a 1 2, okay, minus a 1 1 minus a 1 2 a 2 1 a 2 2. This is 3 by 2 matrix, okay, 3 rows 2 columns. So, we take the transpose of this body matrix. So, transpose of this will be giving you a 1 1 minus a 1 1 a 2 1 and then a 1 2 minus a 1 2 and then a 2 2. Okay. So, subject to constants a 1 1 by 1 dash minus a 1 1 by 1 double dash plus a 2 1 by 2 greater than or equal to we will have, because we had less than or equal to here. So, greater than or equal to C 1. Okay. Then A 1 2 by 1 dash minus A we have here A 1 2, here we have minus A 1 2, minus A 1 2 by 1 double dash plus A 2 2 by 2 greater than or equal to C 2. So, where by 1 dash, by 1 double dash and by 2 are all greater than or equal to 0. Now, let us define by 1 equal to by 1 dash minus by 1 double dash. Since by 1 dash and by 1 double dash are greater than, both non-negative, by 1 is unrestricted in sign. Okay, it is not restricted in sign. So, by 1 then by 1 is unrestricted in sign. And we will get this problem as minimization of, so this will then change to minimization of W equal to B 1 by 1 dash minus by 1 double dash will be replaced by 1. So, B 1 by 1 plus B 2 by 2, okay, subject to A 1 1 into by 1 dash minus by 1 double dash. So, A 1 1 by 1 plus A 2 1 by 2 greater than or equal to C 1. And then A 1 2 multiplied by 1 dash minus by 1 double dash, that is by 1. So, A 1 2 by 1 plus A 2 2 by 2 greater than or equal to C 2, where by 2 is greater than or equal to 0 and by 1 is unrestricted in sign. So, by 1 can be negative as well as positive. So, this is the dual of the given problem. When the primal has equality constants, we will do this. Okay. So, so this is what we have done. This is maximize z equal to this, subject to this. Okay, these constants x 1 x 2 greater than or equal to 0. Then we use the variables by 1 dash, by 1 double dash, by 2. Okay, and we get w equal to this, subject to this. Okay, and which gives us this problem. Okay, the term by 1 dash minus by 1 double dash appears both in the objective function and all the constants of the dual. This will always happen whenever there is an equality constant in the primal. The new variable this becomes unrestricted in sign, okay, because of the difference of two non-negative variables. So, the above dual problem then takes this form, okay, which we have just now seen. Okay. Now, let us consider in general, if the primal problem is z equal to C 1 x 1 plus C 2 x 2 and so on C n x n, subject to these constants. This is equal to B 1, this is equal to B 2, this is equal to B m. Okay. Then it will be replaced with the this dual of this will be minimize W. W equal to B 1 by 1, B 2 by 2 and so on B m by m. Okay. B m by m subject to the constants A 1 1 A 1 1 by 1, A 2 1 by 2 and so on A m 1 by m. Okay. We will have, because it is maximization problem, so we will have less than or equal to, here we will have greater than or equal to, greater than or equal to C 1, okay. Then A 1 2 by 1, A 2 2 by 2 and so on A m 2 by m greater than or equal to C 2 and so on. We shall have A 1 n by 1, A 2n by 2 and so on a m n by m greater than or equal to C m. Okay. C n, sorry, C n where by 1 by 2 by m are all unrestricted in sign. So, this will be the dual. Okay. So, the dual will be b by w equal to b 1 by 1 plus b 2 by 2 and so on b n by m subject to these constants, okay, where these are all unrestricted in sign. Thus, the dual variables corresponding to the equality constants are unrestricted in sign. Conversely, when the primal variables are unrestricted in sign, corresponding to dual constants are equalities. Okay. So, when the when we have equality constants, the dual variables are unrestricted in sign, and if the primal variables are unrestricted in sign, then the corresponding dual constants are equalities. Okay, now, let us construct the dual of the LPP z equal to 4 x 1 plus 9 x 2 plus 2 x 3 subject to 2 x 1 plus 3 x 2 plus 2 x 3 less than or equal to 7 and 3 x 1 minus 2 x 2. So, there is a one equality constant here. So, we have here we can write it as 3 x 1 minus 2 x 2 plus 4 x 3 are less than or equal to 5, okay, and 3 x 1 minus 2 x 2 plus 4 x 3 greater than or equal to 5. We will have to convert to less than or equal to, because the problem is of maximization. So, minus 3 x 1 plus 2 x 2 minus 4 x 3 less than or equal to minus 5. Okay. So, we have the three constants, one is this one, okay, 2 x 1 plus 3 x 2 plus 2 x 3 less than or equal to 7, another one 3 x 1 minus 2 x 2 plus 4 x 3 less than or equal to 5, and third one is minus 3 x 1 plus 2 x 2 minus 4 x 3 less than or equal to 5. So, less than or equal to minus 5. So, the dual problem will be minimization of w equal to, okay, 7 by 1, okay, 7 into by 1 plus 5 into by 2 dash minus 5 into by 2 double dash. Okay. And then we shall have the body matrix is what here 2 3 2, okay, 3 minus 2 4, okay, and then we have minus 3 2 minus 4. So, this is body matrix. Okay. We have to take the corresponding transpose for the body matrix of the dual problem. So, we get 2 3 minus 3. So, 2 by 1 plus 3 by 1 dash minus 3 by 1 double dash, okay, and we will have to put greater than or equal to 4, okay, and then we have 3 by 1 minus 2. So, this should be taken as by 2 and by 2 double dash, not by, sorry, this should be okay. So, okay, so 3 by 1 minus 2 by 2 dash plus 2 by 2 double dash greater than or equal to 9, and then we have 2 by 1 plus 4 by 2 dash minus 4 by 2 double dash greater than or equal to 2. Okay. Or we can write it as where by 1 by 2 dash by 2 double dash, they are all non-negative. Okay. Now, we can write the this problem also in the form minimize w equal to 7 by 1 plus 5 by 2. We will write by 2 equal to by 2 dash minus by 2 double dash. Okay. and then subject to 2y1 plus 3y2 greater than or equal to 4, 3y1 minus 2y2 greater than or equal to 9, and 2y1 plus 4y2 greater than or equal to 2, where by 2 is equal to by 2 dash minus by 2 double dash. Okay. And so, by 2 is unrestricted in sign. Okay. So, the dual problem is minimize w equal to 7 by 1 plus 5 by 2 subject to the constants 2 by 1 plus 3 by 2 greater than or equal to 4, 3 by 1 minus 2 by 2 greater than or equal to 9, 2 by 1 plus 4 by 2 greater than or equal to 2, by 2 is unrestricted in sign, by 1 is greater than or equal to 0. So, this is how we write the dual of this LPP, where one constant is of equality type. So, that is all in this lecture. Thank you very much for your attention.